Hi guys! Today we're gonna talk about a system we built to monitor bedroom environment and measure how well they support sleep quality.
Hi, I'm Warakoli Shawanan.
My name is Ratchabapha Chatakunrak, and we are proud to present SleepSense, a sleep environment monitoring system. Let's get into it.
Most of us know that sleep matters, but very few people actually know why they sleep badly on a certain night. Temperature, humidity, light intensity, noise level, or even air quality can all affect your sleep quality, but they're invisible. You may not feel the 2-degree difference, but your body does. SleepSense bridges that gap. By combining a real-time IoT sensor with user-reported sleep data and published sleep research, we build a system that can quantify your bedroom environment and recommend you exactly what to fix. Here is the overall system architecture. The system is built across 4 zones. The first zone is Field Zone, a kit board with 4 sensors physically installed in the bedroom. Data is transmitted via MQTT to Node-RED, which acts as a central backend hub. Node-RED subscribes to the MQTT topic to write sensor reading to the SQL database every 10 minutes. And from here, 3 REST API endpoints provide data to our analytic layer. That's what we're gonna talk about. And this data then integrated and pre-processed in a Python notebook. We experiment with 6 different models to predict the sleep score, which we will discuss more in detail later. And finally, the Streamlit dashboard pull from the API and present everything in a clean real-time interface. This project involves 3 types of data complexity, and each one requires specific technique response, which is the time series data, multimodal sort, and a small real-world data. We only have 20 real sleep sessions, which strongly affect the pre-processing and modeling decision.
Here are the 3 data tables we work with. The first one will be the sensor table, which is the live IoT REST API. It contains 842 timestamp rows with 8 sensor channels, which are consisted of temperature, humidity, light, sound average, sound event count, PM1, PM2.5, and PM10. The second one is the check-in table, comes from a Google Sheet form with 20 user log entries containing the sleep start time, wake time, and the morning self-reported sleep score on a 0 to 100 scale. The last one will be the research table. The research table is an academic rubric, which optimal environment ranges came from various websites. We expanded this into 30 synthetic sessions to extend the small real dataset.
To integrate them, we match sensor table with check-in table using a time window join. Any reading whose timestamp fall between a session's sleep start till sleep end get tagged with that session ID. We consider this as a real sleep session. We also have to reformat a research table, so it be the same schema as the sleep session, and we call it research session. And here is the working integrated schema before we go the next step. Before any modeling, we ran a structured exploratory data analysis across 6 dimensions, covering sleep daily behavior, sensor pattern, session profile, distribution comparison, feature correlation, and the data quality. Each session answers a specific question about our data. EDA1 looked at the sleep theory itself. Score range from about 20 to 100, with most sessions clustering between 55 and 80, a reasonable spread for regression. Every session duration spanned 4 to 9 hours, and the interesting key finding is the correlation between sleep duration and score is weak. Sleeping longer didn't predict a higher score. It's an important early signal that time in bed doesn't explain quality, and environment factor likely carry more weight. And that finding motivated the rest of the project. EDA2 plot all 8 sensor channel over time with the research idea range overlay as a green shaded band. Reading outside that range are marked in red. And the most consistent finding is temperature regularly exceed the 18 to 20 degrees Celsius ideal. I mean, for a bedroom in Thailand, this isn't a surprise, but it's quantify the exactly how far outside ideal we are every night. Light show periodic spike lightly from uncovered window or brief room entirely, and the PM2.5 and PM10 are occasionally elevated consistent with urban environments. For the EDA3, compare the environmental condition across session, not just overall average, but night by night. We built a heat map where row are sleep session and column are session feature. We have 2 versions, raw-minute version and a 0 to 1 normalization version, so feature with different unit like degrees Celsius and microgram per cubic meter can be compared on the same scale. This will immediately show which night had unusual high or low value across the multiple channels at once.
EDA4 answers an important question of does our real data occupy the same environmental space as the research rubric? This is important because if the distributions don't overlap, mixing them as training data would introduce bias, not coverage. We use overlaid KDE curves laid for actual sessions rule for the research baseline. The result is temperature and humidity overlap reasonably well. For light divergence, real bedrooms have more ambient light than the research ideal result. Sound events are almost near zero in real data, which reflects the quiet environment we monitor. EDA5 examines the bivariate relationship between each environmental feature and the sleep score. The patterns are ranking from strongest to weakest is temperature, sound average, light, sound event, humidity percentage, PM2.5, PM1, and PM10. All top features are negative. Higher values hurt sleep scores. EDA6 checks completeness. We produce a missing value map, a source breakdown pie chart, and a position coverage chart. The positive research rubric rows are always complete because they are constructed values. Real IoT sessions sometimes have missing channel readings, which we handle later via median imputation in the preprocessing pipeline. The source split is approximately 40% in real sessions, 60% in research public. It reflects the deliberate augmentation strategy.
Here is our data preprocessing pipeline overview. We have 5 sequential steps from raw rows to training metric.
Before explaining the pipeline, it's worth to understand why standard preprocessing not fit for our project. First problem is mixed distributional shape. A single scaling strategy can fit all of them. Problem 2, pseudo-replication. The 95 real sensor row conform only to 20 distinct night. Training on the raw row inflate the effective sample size from 20 to 95 by a standard error, and mistake cross-validation meaningless. And the last problem is about the sensor spike, and each of these problems I said is needs specific fix. That's the pipeline.
Step 1. Session level aggregation. We aggregate all sensor reading within each sleep window down to 1 row per session using the median. We should median not mean because it's resistant to spike. A brief light surge from an open door shouldn't represent the light level for the 7-hour sleep, and the result 539 combined row collapse to 50 session level row, 20 real night plus 30 research sessions. Every night contribute equally to training, regardless of how many sensor reading is produced. Step 2. Adaptive log1p transformation. Instead of hard coding which feature get log transformed, we measure actual skewness from the data and apply a threshold of the 0.75. Why this adaptive? Because applying log1p to sound average, which negatively skew at the -1.29, would add asymmetry, not remove it. The check prevents that mistake automatically even the dataset grows.
For features that don't need log transformation, we clip each one to its 5th to 95th percentile interval. We build this as a custom scikit-learn compatible transformer from scratch. It fits only on training data, so test set percentile values never dominate the clip boundaries. StandardScaler is different from Winsorization because it rescales outrider but does not limit their inference. A sensor spike at 1000 routes still pulls the distribution. On the other hand, Winsorization explicitly caps extreme value before scaling. After Winsorization or log transformation, all features pass to RobustScaler, which normalize using the median and interquartile range instead of mean and standard deviation. This makes it resistant to any remaining outliers. The two preprocessing parts, which are the log skew block and the linear block, are assembled into a single ColumnTransformer. Each feature gets the right treatment inside one clean scikit-learn pipeline with no leakage between steps. StandardScaler on the raw sensor table of 842 rows could place reading from the same sleep night in both train and test. We use GroupShuffleSplit with session ID as the grouping key. Every session runs in exactly one partition. This gives us approximately 32 training sessions and 18 test sessions.
Step 6. Training data synthesis. With 32 training sessions, 3 assemble easily overfit. To reduce overfitting, we apply two augment methods, SMOTER and KNN synthesis. Both generate additional training sessions based on existing data. We test them at multiple 3 and multiple 5 level across 6 models.
We compare 6 regression models, all using the same preprocessing pipeline. The first model will be linear regression. Sign coefficient map directly to lower temperature, so it leads to a better score. But without regularization and only 32 training sessions, it's so unstable. For rich alpha 1, it shrinks all coefficients, while rich alpha 10 handles correlated features like temperature and humidity better. Next, Lasso can zero out raw signal features entirely. It is useful for testing whether the PPM channels are truly unnecessary. Gradient boosting has shallow depth and low running rate, but it acts as strong regularizer for small datasets. And the last one will be random forest. Random forest examines a pattern which no linear model can represent.
For explainability, we use SHAP or sharply additive explanation. SHAP decomposes each prediction into a per feature contribution. Every feature gets a side value for a specific night. Positive means it pushed the score up, and negative means it pulled the score down. The explainer type is selected automatically: tree explainer for random forest and gradient boosting, linear explainer for ridge and lasso, and kernel explainer as a model agnostic fallback. Looking at SHAP important across a 6 model, temperature is consistently the top or second ranked feature in 3-bit model. Humidity and light dominate in linear model. Sound average appear across all model types. This cross-model consistency keeps us confident. These features are geniusly informative, not artifact of one model behavior. SHAP is also what powers the recommendation engine when the system say, temperature is dragging you down by 30 points, try lowering it. That's a SHAP value turned into a human-readable action.
Here are the results across all 30 model scenario combinations, evaluated on real test session only. We use MAE for intuitive point error, RMSE for penalizing rush errors, and R-square for explained variance. Without augmentation, gradient boosting reads at MAE 9.2, random forest at 9.1. Linear regression without augmentation reaches MAE 35, which is too high to be useful. With best augmentation per model, random forest plus SMOTER for regression times 3 leads to MAE 7.73, which is the best overall result, a 22.5% improve over its baseline. Rich alpha 10 plus SMOTER for regression times 3 leads to MAE 13.66, which is best when interpretability is considered. All 6 models benefit from at least one augmentation scenario, and linear models gain the most in absolute terms. This residual heat map shows prediction error per session per model. The pattern is clear as certain nights are harder to predict. Linear models show residuals up to 40 up points on those nights. Random forest and gradient boosting handle the same session much better. This suggests those nights have conditions where multiple factors interact in a non-linear way, which 3 models capture through their split structure, but linear models simply can't represent.
Now, let's look at what this looks like for end user. The Streamlit dashboard wraps the full pipeline. On load, it fetches the latest reading from the live REST API. The sidebar lets you choose from 6 models. You can also switch to manual slider for scenario testing. The main panel shows a real-time snapshot chart of the sensor channel over the recent period. A sleep score gauge from 0 to 100 with color-coded quality band. A SHAP impact bar chart, yellow for factor helping your score and red for factor hurting your score. And the actionable take recommendation here, as you can see. The output is designed to be immediately helpful, not just number, but the reason and the next step. Beyond personal use, this pipeline scales naturally to survival domain. For example, like smart bedroom automation, auto-trigger the thermostat and smart blinding when SHAP predicted a poor night. Hotel and hospitality per room profiling and automatic comfort preset based on the guest history. Or like building energy management to balance their sleep quality against HVAC energy cost using SHAP marginal value.
Let's wrap up. SleepSense shows that meaningful sleep quality prediction from environmental data is achievable when the preprocessing is handled carefully. Preprocessing decisions matter more than model choice. Session aggregation, adaptive skewness detection, Winsorization, GroupShuffleSplit, and data synthesis each has a larger impact on final MAE than switching between models. For data synthesis, it works, but it's model dependent. Smooth for regression helps random for length significantly. It can hurt gradient boosting, and there is no universal augmentation strategy. And lastly, SHAP turns a number into an actionable recommendation.
And that's all for today. Thank you for watching. SleepSense, Intelligent Sleep.